that original limit was equal to the limit of each of those guys what? No, each of those guys what? Derivatives, right? And then see if I would get an answer. If I got 0 over 0 again, I have to go through the same process again, and I have to show all that work nice and pretty. They don't accept you writing just equals to 0 over 0. So be careful, okay? So here we're going to L-hop it, okay? Now we're going to do it MC style. So we're not going to show all that stuff, but know that you're supposed to on free response. So we'd end up with the limit as x approaches 0. What's the derivative of the numerator? 1 plus x
plus
over? Is it over something?
no
No? Okay. Is that it?
x squared over 2 x
X squared over 2? 1/2 x squared? The 3 would be in the front, and we'd have x squared, right? And then this 3 factorial is 3 times 2 times 1. So the 3 would go away, but you'd still be left with the 2 times 1, right? Which is the 2. You see it or no? Okay. Divided by the derivative of the denominator, which is? And what would this limit equal now that I evaluate it again?
2 I mean 1/2
1/2, right? Now, did we use e of x?
no
No, right? We used a small polynomial that was an approximation of e to the x, right? Let's see what happens if I actually work it out using e to the x. Okay? Let's see if we get the same result. What do you think? Are we going to?
yes
So try it out. Plug it in. Plug in 0. What do we get? 0 over 0 again, right? So that means we can do what again? We can L-hop it. Right? So we're going to L-hop it, and we're going to get the limit as x approaches 0. What do we get for the derivative of the numerator? And the denominator? And when we evaluate it? Woohoo! Pretty cool? So was it a good enough approximation? Yeah, it was good enough, right? Just to go to third degree to be able to get an equivalent answer. Okay.
If the limit, if it was like, if it equaled something like really big, would you have to approximate it further?
What do you mean?
Like if the limit equaled like 100, would you have to approximate e of x further?
Yeah, you'd have to get a center closer to 100, right? Good?
Good.
Actually, with e to the x, you probably wouldn't have to. It's just that the approximation going up to a third degree polynomial wouldn't be as good as the one with a larger polynomial, right? Because the further, the bigger the polynomial, the further out the curve is going and matching the behavior of the other curve. Does that make sense?
Yes.
Okay, now the polynomial that we generate for e to the x will match it perfectly if I were to draw the infinite one. Okay, the radius for e to the x, okay, using the polynomials is infinity. So you could pick any x you wanted to and plug it into that polynomial, and it will give you the value of e to the x. But it would have to be the series, it would have to be the infinite polynomial. Does that make sense? Sort of? Yeah?
Yeah.
Okay, cool. Alright. What does the next one want? This will be the last one, because we're running out of time.
Can I read it?
You want to read it again?
Yeah.
Alright, go ahead.
Let f of t be a function that has derivatives of all orders for all real numbers. If f of 0 equals 5, f prime of 0 equals -3, f double prime of 0 equals 1, and f triple prime of 0 equals 4. Write the third degree Maclaurin polynomial of f and approximate the interval. I can read that.
The integral, right? From -1 to x of f of t dt. Okay, so what do they want us to do here?
Write the third degree of Maclaurin.
Write the third degree Maclaurin polynomial, and then do what to it?
integrate
And then integrate.
Integrate it, right? From -1 to x. Okay? So, what are they giving us to be able to create that Maclaurin polynomial?
The center.
The
The
coefficient.
center? What's the center?
Zero.
So the center is 0 because they said it was Maclaurin. So that means we're not going to have c x minus anything, it's just going to be x, right? Okay? And they're also giving us the what? The numerators of the coefficients, right? So it should be easy to create, yes? So let's do it. So f of t is going to be approximately p sub what? Sub 3, and we're not going to use x's here, we're going to use t's, okay? Because when we integrate it, they want us to integrate it with respect to what? To t, so we want the variables to match, okay? So what would we end up with here? What's our first number going to be? 5 over 0 factorial times x to the? Oh, not t, right, Jason? It's t, so t to the 0. Good thing you caught it before we continue. And then? Minus 3 over 1 factorial, t to the first. And then? 1 over 2 factorial, t to the second. And? T to the third. Good? So they want us to use this polynomial in place of f of t, and they want us to integrate it from -1 to x. So can we? We haven't done integration in a while.
Yes.
Should we simplify this maybe before we try to integrate it? Yeah, let's simplify it, right? Get rid of those factorials. So what would this become? 5. And this? 3t. And then this? Half t squared. And this?
2 over 3.
2/3
Yeah.
t cubed?
Yeah.
Yeah, because that would be a 6, right? So 4 over 6 is 2/3. Are we good? So now it looks like a simple polynomial, one of the very first things that you probably learned to get the integral of, right? Yeah? And you're just integrating it, which is super simple. So let's see if we can do that. Let's see if we can flash back to calculus AB and remember how to integrate these little babies. So -1 to x, and we're integrating 5 minus 3t plus 1/2 t squared plus 2/3 t cubed with respect to t, so dt. A lot of you forget to put this on your stuff. We're trying to train you to be good mathematicians, right? To write proper notation. So practice. Good? All right, so let's do it. Let's see integral of 5 with respect to t. 5t, good job. So far so good. And then? Minus 3 over 2t squared. Remember, we add 1 to the power and divide by the new power. So what's the next one going to be?
T over 6 to the
3 over what?
or
1 over 6.
1
1 over 6?
T squared.
T to the what? Why is it 1 over 6, James?
because you
What do we do to this guy?
add 1 and
So
then
that's
divide
t
by
to
the
the third?
reciprocal.
Right? And we don't divide by the reciprocal, we divide by him, right?
Yes.
So we divide by 3, and it's divided by 2, so 3 times 2 is
6.
6. Good? Alright, how about the next one? 1 over 6 also?
Yes.
T to the what?
4.
Plus c?
No.
No? Why don't we need plus c?
We have balance.
Because we're evaluating it, right? It's a definite integral. It's evaluated from -1 to x. Alright. Let's finish strong. So what do we end up with here? Which one do we plug in first? The top bound, right? Following the fundamental theorem of calculus? The fundamental theorem of calculus I love, right? This is it. Okay? So plug in x. What do we end up with? Oh, finally we get the x's back. So basically the letter just changed, right? Oh, they're so nice. Still the same girl, just added makeup. Okay? Okay, and then we're going to minus what we get when we plug in what? Negative 1. What's going to happen when I replace the t's with negative 1?
Then you switch sign. Oh,
Some things are going to switch signs, right? Which ones are going to switch signs?
what's
The ones with an odd power, right? So the 5 would become a negative 5. Would this one change? No, that's still 3 over 2. Would this one change? Yes, minus 1 over 6. Would this one change? No. So the value doesn't change, just the sign, right? Like my last name, sign. So what goes away? 1/6, can we actually add those two together? Common denominator would be what? 2. Negative 5 times 2 is negative 10 minus 3. Negative 13 over 2, but then they minus it, so it becomes plus 13 over 2. And then we basically just bring all this down, right? Because there's nothing to put him together with. Cool? So they're combining the new idea of Maclaurin and Taylor polynomials and asking you to do stuff with them, like I told you yesterday. Integrate, derive, by the limit, anything you've done before, but now with these things. Good? We'll stop there? Alright. Tomorrow we'll continue. We'll finish. Let me give you the assignment. You can get started on it.